Hello everyone, welcome back to First Principles Engineering. Today we are going to cover chapter 2 of Inference Engineering book by Philip Kiely, and today will be the part 1 of the video. The book contains only chapter 2, it doesn't have any partitions, but to make the concepts clear and get into a proper depth, I have divided the chapter in two parts. One is for text generation and one is for image generation part. This chapter gives you the high level view of different model architectures and how these can be optimized. What are the different variations of attention mechanisms? So, but this book doesn't provide any implementation of code or any other thing, or it doesn't even explain the clear mathematics. But as the goal of our channel is clear to have a deep dives and learn proper engineering instead of just modifying things. So I have implemented a few attention or transformer architectures and a few MOE architectures. I would like to show them and explain those along with the code. So because of that, it's taking it the lecture might be big. So to avoid confusion, I have divided this chapter in two parts. Today we will cover text generation models, and in the part two we will be covering about image generation models and video generation models, which will include variational autoencoders and diffusion mechanisms that we will see in the part two. So also I would like to bring into the note that I have recently posted a post on YouTube regarding the suggestions for the next book. I have given the four options. I would like you guys to choose one of the book, or if you have any other suggestion, please feel free to comment. As I also need to prepare before creating the lectures, and today, anyways, we will be continuing inference engineering till this book is completed. But I need to obviously prepare for that lectures also. So it would be great if you guys can provide a feedback and help me in choosing the next book. Otherwise, I will be choosing randomly from those four books because I feel those are interesting books. Anyways, let's get started. Uh, yeah, mostly you guys might have seen many LLMs and like ChatGPT and Anthropic, all of them have their own features, own reasoning mechanisms, etc. Today we will have deep dive on it. Everything or every architecture is based on this research paper, which was released in 2017. This is the research paper. Attention is all you need. I would highly recommend you guys to read this paper. And if you guys are not able to read other papers, then it's not a problem. But at least and at most priority, give to this paper. Don't leave this paper. I feel that every person interested in AI or interested in contributing to different LLMs and thinking at that level should read this paper first. Uh, I understand reading this paper is a bit difficult and requires a good grasp or control over mathematics, but you can take it from AI and learn these things. I would recommend reading this paper. It was by Vaswani, released by Vaswani and other team. Next, I think you guys have. Yeah, this is the post which I want to show. I hope this post many guys have seen uh, the life before this paper released and life after the paper released, etc. So this is actually the truth. AI became very popular after this mechanism. Today we will have a deep dive in this architecture and different variants of this and different optimization techniques of work. Firstly, the transformer, the transformer which I've shown you recently in attention is all you need. Mostly we can divide transformer into categories: auto-regressive token generation and iterative denoising. Mostly auto-regressive token generation is for the is it means that generating the next token in the current text. If you have one, if you have three words, then generating the fourth word comes under auto regressive token generation. It also means that the while training, the current token doesn't see the future words, it only sees the previous words. It generates the next word by seeing the previous words, and this word is again appended to the sentence, and the same process is carried over by the new token till the end of token end token comes out by the end. This is mostly auto-regressive token generation. We will deep dive how this happens mathematically. And next is iterative denoising. It is mostly used in image and video generations, where where the model starts from random noise and tries towards or tries to add meaning and keeping different stuff on it to generate an image. This is mostly via diffusion mechanism and BAE, variational autoencoders. This will be the topic of part two of chapter two. Not today. Today we'll be mostly focusing on this part, auto regression token generation. Next, I would like to say you. I would first like to give a brief about neural networks. I hope everyone knows neural networks, but still, I would like to give you a high-level view. Neural networks. Two, three, one, three, one. Okay. This is generally called as input layer, and this is called as hidden layer. Uh, Hidden layer, and this is called as output layer. There can be any number of hidden layers in between. Currently, I have only one hidden layer with four neurons, and let's say all neurons are connected to each other. Yeah, imagine all neurons are connected from one layer to another layer. And these are the weights of this. What this means actually is, for example, uh, I have an input of the size 3, or I can say that I have an input which have some three blocks, you can say. It can be now generally in images, this input can be instead of three, it can be any number, which are the number of pixels. This can be that, but current now let's say we have three input things or input features, we can say f1, f2, f3, f2, and f3. These three are given as input, and based on these weights, they interact with the hidden layers, and this value generated by here interact accordingly with the last layer. Here, let's say I have two things which you can get. Let's say it is a classification model. I gave three things or three parts as input. As I said, it can be audio, video, text, anything. We will see this, and output. Let's say we have cat, and if the last value, let's say the last value of here is 0.1, and of this neuron is 0.7 after the whole, or 0.9, sorry, as after the whole mathematics performed or matrix multiplication performed in the previous layers, the final value comes out to be 0.1 and 0.9 for the dog. You can see that the sum of these both is 1. This comes from a softmax function softmax function, which is used to divide, or we can say that which is used to make the sum of all particular values equal to 1. Because let's say if the value generated by the value of this neuron is, let's say, 2 and this is 3, then the probability distribution or values are not correct. 2 and 3, this cannot be probability. So we apply softmax over it, over the whole, these both values, and we get probabilities of the output being as cat and probabilities of output being as dog, and we select the maximum probability mostly. But we have different approaches like top p and top k, which we will discuss now. And also softmax formula I would like to show you, it is e power pi, which is probability of the ith output divided by sigma of e power I I want to say j. It would be probability of j, sum of probability j, where j is from 1 to 2, because here we have two output neurons. So after applying softmax on the first number, let's say that is 2, the number generated by neuron is 2. After applying the this softmax over it, it will become e power 2 e power 2 divided by sum of e power or e power 2 plus e power 3. Similarly, probability is also generated for the second one, which then it will become e power 3 for the second output neuron, that will become e power 3 by e power 2 plus e power 3. This is the softmax function which you will apply to get the values between 0 and 1, or we can say that probability distribution of all values. This is the softmax which we apply. So on the whole, this is the neural network. Here, whenever we get some value, we will check with the expected value. Let's say let's say this neural network generated the output as dog. Let's say it already generated at 0.9, which means that the given input is a dog. But how do now what we will do? We will check whether the it is correct or not. How to check that? We know whether it is dog or not. If it is cat, then we will do. Let's say we have confidence of 100% that it is cat. Then we will do subtraction. What is that? L, or we can say that we can use different loss functions like mean squared, or different are there. If here we want to generate for a loss, if here we want to know the loss, then it would be what we say predicted value minus actual value. Predicted value minus actual value. So it will be p minus a. Predicted minus actual value, mean squared error. Or we also have this one more method, just subtracting predicted minus actual and doing otherwise doing as mean squared error. You take the mean, apply square over this value. This is mean squared error. We have different mathematical, or we can also design if we if we have something different we are performing, then we can also design our own mathematical loss function, which will loss function basically just tells the difference in the expected output and the actual output. So once this loss function is calculated, or the loss is calculated, then we back propagate and update these different weights here, and again the forward propagation happens. Again values are generated, again we will calculate loss, again we back propagate. Like that we run different number of epochs. Epoch means similarly is simply one cycle. One forward plus one backward is equal to one epoch. Like that we run we can run n number of epochs based on the compute we have and based on the amount of data we have. So this is how the plain neural network works. It has input layer, hidden layer, output layer, and each layer produces an output for the next layer, and the output by previous layer is input for the next layer. These weights are also called as hidden states, which are hidden states, and these are updated by backpropagation. Backpropagation, I would love to take you guys to deep dive of backpropagation, but then this lecture will be too long already, because we are going to cover many architectures and many different optimization techniques. So I would like you guys to explore on yourself, because this is not a tough part. Most of the colleges also teach backpropagation and and these neural networks. And I have seen many people only know these things at least. These are the basic building blocks. So I won't waste your time on this part more. This was just a high level introduction of what neural networks are and how they work. Next, we have tell you about in this neural network. We also have, I forgot to say you, as these are linear layers, we introduce different loss functions. No, sorry, not loss functions. We introduce different activation functions in between. Uh, this help in getting non-linearity of, I would say, what is non-linearity. Now, this neural network generally calculates a line, a best fit line on our data which we have. Let's say we have a data of a few circles and few squares. Then this neural network will try to fit a line in between of this. And whenever next time we give the input, let's say the input is circle, it tries to check on which side this circle belongs to. If the line is fitted, it tries to check which side of this input belongs to. If this input belongs to this side of line, then it is circle, and if it is at this side, then it is square. That input which I gave. This is how mathematically neural networks function internally. They try to fit a line on our huge data. So our job is that this line fits in a way that we get a good accuracy whenever we give any input. Now, the complexity arises when in data we have many shapes, and it is it will be completely impossible for us, like this. Here are few circles, here are few circles, and here are few squares. So in this kind of data, it is highly impossible we fit a straight line so that we can get which shape belongs to which part or which cluster. It is highly impossible to fit a line. So here we would like to introduce non-linearity. Means this line bends, or this neural network learns patterns to bend this line accordingly, so that we can fit the line in a way that we get the accuracy. So to introduce this kind of non-linearity, we introduce activation function. Originally, as you guys might be knowing, the equation of any line will be y is equal to mx plus c. Here m is the slope of the line, c is the intercept, x is the input, y is the output. Correct? And for this line, as it passes through origin, intercept will be 0. So the equation of this line will be y is equal to mx. Okay. But we want non-linearity. So here we introduce different activation functions, like the most popular activation function, the ReLU, leaky ReLU. Formula of ReLU is generally max of 0, comma x. This is the formula of ReLU. It means that, let's say I have input of 1. I am giving number 1 as input. Example. And if we gave input of 1 to this function, then the output will be 1, because max of 0 comma 1 is 1. Let's say if the input is minus 1, and then the output will be, what will be the output? Max of 0 comma minus 1, which is 0. So clearly here we can think and plot the graph for what is a ReLU. Let's say this is y-axis and this is x-axis. Here is the origin 0. Then the graph of the ReLU will be this, and all the negative values of x will become 0 and the positive values remain the same. This is the graph of ReLU. These are used to introduce non-linearity in between, so that pattern identification becomes much more complex and the final output becomes much more accurate. So I would say that here in a neural network, I have a few input layers and one output layer. Okay, this is input, this is output, and there are two input layers. Here in between, we attach different activation functions in the ReLU or leaky ReLU. In leaky ReLU, we multiply this function with a small value. Let's say it as 0.2. This avoids the, now this will be the leaky ReLU. This avoids, as you can see, that negative values are completely every time becoming 0. But then we lost the data, like we forgot or we don't know. We are treating at this point in ReLU, we are treating -1 and minus infinity also 0, which is obviously not correct. So we don't want to completely damp out the value, so we multiply a small multiply the value with small factor. It can be 0.1 in leaky ReLU, so that graph becomes this. Then this will be the graph. Yeah, it provides it doesn't damp the value completely. You can browse these things and see. I would highly recommend you guys to see. This is leaky ReLU. ReLU leaky ReLU. We multiply with a small factor 0.1 or 0.01, so that the value, all negatives are not treated equal to 0. Different negative values of a, we know how what value is how much or how negative it is. So we use leaky ReLU. But these depends on different use cases. It comes by experience or comes by trial and error. By trying on few neural networks, you will understand what effect each function or mathematical combination is causing. At different layers, we use different activation functions. Mostly, I've seen that on final layer we use softmax. In between, we use the ReLU or Wiki ReLU or GELU. GELU is also there. I will show you that. So GELU. This is GELU activation function. As you can see, this introduces non-linearity in our pattern or in our neural network. TANH is also there. Many activation functions are there. I would like you guys to see these activation functions and try to understand them, because these will be going to be the base for different AI applications as we are growing in AI. If you guys want, then I will take a deep dive into basics and nuts and bolts of neural networks. If you guys are interested, please comment regarding this. But currently, let's stick to our inference engineering instead of getting deviated from the topic. Now, I showed you what is a neural network, what are activation functions, and what are input layer, output layer, and hidden layers. Let's get into inference mechanics of LLMs. Mostly, when you're inferencing an LLM, here you guys will have two or three kind of things which you need to think, like on let's say what to give it as input sequence to LLM, and what are the, or we can say that what is the input sequence or context. This is input given as input. Any system prompts also come under this, or any guardrail prompts or anything comes under this input. And output sequence is what LLM generates as final output. But nowadays, as you are seeing reasoning LLMs, they show the thinking steps also. So that is called as reasoning sequence. These are also, these are also considered as output of a LLM. It always outputs the tokens what it thinks, what it thinks, and based on those sequences, it produces output tokens. We can output these also. These are the finally output. So mostly these three things we will check. And the LLM inferencing, I would say it is mostly in two phases. Let's say I have an LLM and I gave it some input. Then, firstly, I would divide this as in two phases: prefill phase and decode phase. What are these two phases? Prefill phase is when we give the input and the processing that happens, like generating KV cache, generating what we say in different mechanisms. In some mechanisms we have KV cache, some mechanisms we have different architectures of attention, which we'll discuss now. Those things come under prefill phase, and the final output generation, or the next, whenever we see the next token generation, that comes under decode phase. So the book clearly states it as process the input sequence, calculate attention for each input, and tokens, store them in KV cache. These part of LLM comes under prefill phase, and rest, the second half, comes under the decode phase. I will not say what exactly. I will not say now what things exactly come under prefill phase, because I don't think so everyone might be knowing attention mechanisms. So I will, once if I show you the attention mechanism or I explain you that, I will explain. Then I can explain the prefill phase more clearly. So let's continue. Yeah. Now let's get into attention mechanism, which is the most uh, important in this LLM era. Yeah, this is the attention or transformer architecture which they have introduced. This architecture, as you can see, the left side is encoder, the right side is called as decoder, and these are the inputs. Inputs means the sentence we give as input. This is that, and we create input embeddings. After the input embeddings are created, we create positional embedding. I will explain you everything. Then we go through multi-head attention. This is the most important or crucial part of attention or LLMs. All the reasoning and thinking which we are able to see in LLMs is because of this block. And I would say that this block is the only, or not only, this is the block which requires the highest amount of GPU and RAM. Due to that, we are seeing the shortage of these things today. This is the main heart of the attention or heart of the transformer block. Then we have a normal feed-forward neural network. Feed-forward is same like a normal neural network which we have seen now, which had three inputs and uh, two outputs. That is feed-forward. That, and these are the normalization and addition kind of things which are introduced to avoid the spike of values in between. Then we get into decoder. Decoder we have, as you can see in decoder, we have masked multi-head detection. Once here, I would like to concentrate on important thing. As you can see, we have encoder and decoder here. GPT architecture, when you see it, it is mostly based on decoder, or it is only decoder based architecture. Chat OpenAI have removed this left side block, decoder block, completely, and they have stacked many layers of this right side decoder block. Input goes in here, some processing happens, which we will see now, and that processing happens in n number of these layers. As you can see n here, n number of layers are there. In GPT there were 96 decoder or this layers, and each layer may have n number of attention heads, multi-head attention heads, and feed forward. Then finally softmax, as I said, mostly softmax is applied at the end of the neural networks because it helps in generating or getting the probability distribution clear. First we will see input embeddings, positional embeddings. Okay. Current, uh, let's say we have a sentence: I am AI we have this sentence with only three words. We give this as input. So here that will be the input. Here that sentence will be the input. Next input elements. We create. Firstly, I would say we would tokenize. Tokenize is we break down or chop off this sentence to different tokens. Tokens are just, you can say, think of it as word, but it is not completely a word every time. For example, if I have a word swimming, okay, swimming, SWIMMING, swimming. Then when generating tokens, we break SWIM, that is one token, and ING is other token. Okay, we break down this, and there is an algorithm I will show you normally. Byte pair ANC only. This is one algorithm which even ChatGPT uses to tokenize the input sequence. They break down the word into chunks, or we can say that different understandable words to AI. I would like one thing I would like to highlight that why are we not considering swimming as one word? Because then if we add one more word in our vocabulary like swimmer, then again it will be a new token. So many, we can say swim, swimming, swimmer, many things we can say, and each of them becomes one token in our vocabulary, which is not correct. And let's say we have only vocabulary of three words, and the person tells one more type of swim, or something new word related to swim. Say swims. He introduces swims in our vocabulary. Then our vocabulary won't know that. Again, it will be a problem. It will become as NA. मतलब AI would treat it as NA token, which is not applicable token. Something of that sort. So OpenAI have decided to take a word and break down into smallest understandable word. Like how this problem, which I told you now, is solved using this is in byte pair encoding. We have a word we break down like we broke swimming to swim and ing. SWIM, swim, and ING, swim and ing. We broke it down to two tokens. Let's say the person says swimmer, then again swimmer mein we the LLM would get swim already, and ER will be remain. At least the model will be able to understand the context or what the word means. It would not completely give NA there. Instead it will understand what the person wants to say, or what the actual meaning would be. At least that it can understand. And because of that, we are using less tokens also. That NA part is encountered and is fixed. And one more thing is that we use less number of tokens for all the words related to swim, swimming, swimmer, swims. Only one token is required, swim, and ing, and these things are considered as different tokens. And this ing and these can be used for other words. Let's say I'm telling skipping, then ing comes from here, and skip will be the other token. So this one ing is used or can be used for many tokens in constructing many tokens. So we are using, we need to, there's no need to maintain a huge vocabulary. And also the new word problem is also solved using byte pair tokenizer. Simply it breaks down into smallest understandable part. I would like to say you to see this byte pair encoding articles on different platforms. Many people have implemented it. Sebastian Rasa have implemented it. I won't take this lecture towards there because again it is a big thing to introduce. But yes, I would recommend you guys to explore because I feel that exploring things will teach you more than I can teach you in this 1 or 2 hours. The only thing I would say that keep questioning and keep understanding more things at its to its base level so that you become a good engineer. Whatever I teach here, it won't be sufficient for your career because today the world is changing a lot. We are seeing every day some new architecture, some new LLM or some new methodology of using LLM. Because of that, if you guys don't know how to learn or how to search or how to adapt in these fields, then it will become very difficult to survive in this industry. I will teach you how much ever I can, but there is a bottleneck on it because each and everything, if I try to explain only in attention mechanism, it will easily take me about what we say more than 10 to 20 lectures. If you take me, I may take one lecture on input embeddings, different architectures or different algorithms for creating embeddings, different models of input embeddings. Then I would say some different mechanisms for each part. It will take more than 15 to 20 lectures. And currently, our topic is inference engineering. The book doesn't even cover these many things at depth, but still, I would like to at least tell you guys how the things function instead of just giving high level view. I should cover the book part, also inference engineering part, and also extra parts, which costs me a lot of time. Yeah, input embedding is first we tokenize our sequence, input sequence. Let's say here that a good scenario, one word is one token, and this is one token, this is one token. I have three tokens like that. Then the embedding for each token will be created. Embedding is just the high dimensional representation or a vector representation of a token. Okay, it can be of any dimensions. In initial stages of ChatGPT, many initial LLMs had this about, I think, 256 or 1024, maybe I don't remember the number. The size of this vector was 1024, I think. This vector is nothing but uh, different floating point numbers are there here, 0 0.1, 0 0.8, and these numbers are there here. This is just the embedding of I. Like that, n means 1024 in initial stages. Now I don't know because they don't have any paper or research paper released for ChatGPT 3. I think after ChatGPT 3 they have stopped releasing the papers. Okay, so like that 1024 numbers will be there for I, and this is the vector representation, means n dimensional representation, means in one dimension I have this point, in other dimension I have second point, like that. Like that, it is n dimensional. It is impossible to visualize n dimensions. I can only show up to three dimensional x, y, and this is z, that is towards coming to you. But there are total n dimensions like that. Why is this beneficial? First of all, these embeddings are what we say. Let's consider it in three dimensions. Let's say x dimension represents the character, or let's say it represents gender. These are automatically defined while training models to generate embeddings by huge amount of data. We can't say that zeroth dimension here refers to gender, first dimension refers to some other capability. We can't say that. It is impossible for us to say. Let's say y represents the status, status status, and third dimension maybe represents something else. Then let's say I have a I vector. It is somewhere between. Let try to visualize. It's in between three dimensions here. Then it has z some value, y ka some value, and x value is something. Then here, as it has some part of everything, it represents or it has capability of something of some dimension every time. For example, if I have a vector for queen, and I have a vector for male, and I have a vector for I this should be plus, and I think this should be minus. And I have a vector for woman. These vectors, woman. These vectors come in the output. If I do this mathematical operation, queen vector minus my plus male vector minus woman vector, then it will be a vector which will be similar to king, king vector. I hope you guys can visualize because each thing represents one dimension. Let's say this vector represents uh, woman, and let's say this vector represents male. Then subtract. Then yes, sorry. Let's say this vector represents woman, and this vector represents queen. Then subtracting these both vectors together, how to subtract vectors? Simply woman vector, and as you want to subtract the queen vector, we will directly flip it 180 degrees. This is queen vector, and the net vector n vector, this we will be getting this vector will which we will get as result of these both. This operation will obviously negate the woman part from the queen, and when we add male to this net vector m plus m, then again how we will add, this is the male vector, let's say. If we add a male vector to it, then again we take the net vector. Now as it is addition, no need to flip, then you will get one single vector. This will be king vector, as the value of male got added to this net vector. Okay, so these things are not covered in book. These I just told as extra knowledge, just so that you can visualize what a vector is. Nothing more than that. If you guys didn't understand that, no problem. This won't be a blocker for inference engineering book. But try to understand and try to learn more from AI and different platforms, etc. Okay, so this is what is input embedding. We create input embeddings for our three words, which are ND vectors. I told you what the vector is. I tried to explain you. And then we add positional embedding. You can see this plus symbol. We add a positional embedding. Positional embedding are again a new set of vectors which are added to these vectors. Plus, plus, plus. These position vectors can be trained separately and brought onto our mechanism, or it can be trained in the complete architecture. Like this is one forward pass happens, and when the backward pass happens, here only position the model which generates position embeddings or the position embedding tokens, what we say, position embedding vectors are trained here itself in back propagation. That is completely on you guys, or generally people prefer it to train along with the architecture only, so that it learns from the current input output requirement. So this is one, and these are added. What these vector does, these vectors, like I said, each vector has some knowledge in different dimension. So these vectors mostly have more knowledge of the position of a word. Like I said, I am AI here. Then this position vector will have the knowledge of the position of I. So when we are adding it to our input embeddings, then in our embeddings, like I said, if we add two vectors, then the net vector coming out will be sum of these both. So this will have knowledge of both. So when we add these both, then the net vector which we will get here, this vector will have knowledge of both I as well as, say, position of I in the current sequence. This is one way, or else the original attention is all you need. Paper gave formulas which are not used anyways. So if you want, you can see that in paper, sine and cos formulas they gave. If it is in even position, then some formula will apply. But that is not useful now because it is better to get this vector knowledgeable or give them a knowledge based on our context or based on our training data instead of using some other vectors or some other formulas. These became extra parameters for us, which helps us to make the output of LLM better. So this is one part that is added here. So the vector that we'll be having here at this point, here the vector which we have will have the knowledge of the word, as well as knowledge of the word means what I means in general sense. In this, it is not, this first vector is not about what I means in this sentence. It is about what I means generally in English. So this is that vector, and this is positional embedding added. So now the net vector has the meaning or the knowledge of what I means in general sense and what is the position of I, because the position matters here, because the placement of word also defines the meaning of the word. So we add position embedding here. Next, we have the hard part, which is attention mechanism. Here, I would like to show you. Now, once we have this resultant vectors of three tokens, these, what we say, these embeddings now are passed through attention mechanism. What is attention mechanism? The attention mechanism is the way when the words understand each other in a sequence. Like I have I am AI. Then here AI. Here each token will try to understand what other token means and what value they add to AI. Here, think that you are in the position of AI here. According to you, I and am, when you see back or right side of yourself, you will see that I and am are telling that, what we say, are telling you some information about the past, or whole sentence. Like uh, here, if you are at the position of AI, here I and am will tell you that the person trying to speak this sentence is referring themselves as AI. If you are at position AI, you will think that. If you are at position of am, then you will see I and as well as AI. Then am will learn here from the other tokens. I'll show you how this is done, but this is what is the main concept of attention here. Because of this only we got LLMs so intelligent, because each token or word is able to understand what the previous words are telling. It has context, so it is able to think in that way. Now, the paper introduces, yeah, there are many ways. I would say there is a naive way for doing this part, which is discussed in, what we say, Build LLM from Scratch book by Sebastian Raska. I'll show you that book also. Book by Sebastian Raska. Yeah, this is the book. This book gave different approaches of using this mechanism, and it showed a few drawbacks also. Then it showed how we came up to the formula or attention mechanism shown in the attention is all you need paper. If you guys want, I can do the or I can take up this as the next book. Please vote or say which book should I take as the next one. Yeah, that book has some methods, but now currently I will show you the best method which is introduced in the paper to know what other tokens contribute to me, what I have learned, what I have to learn from them. They have introduced a formula. I would love to explain the mathematics behind this formula, but currently our topic is inference engineering, not designing LLM from scratch. So I won't take much time on this. The formula is Q K T. K transpose is KT Q K T by root D. D here means dimension of our vector, or the vector which we got here in input after all the things. And, or a dimension of key, we can say that this is that, and Q K T into V. This is the value vector. Let me explain you each thing properly. Let's imagine we are at the position of AI. Here, AI will make its own Q, K, and V using WQ, WK, and WV. These are the three trainable matrices in the transformer or attention. We train these matrices, and let's say the token embedding of AI is X. Then we do, to generate Q, we do X into WQ, and these are same as how we train neural network. These matrices are also trained in the same way. Nothing magical. We don't define anything. We just define these matrices and let them train in the whole process. I will show you in the code also. And K is again X into WB, and V is X into, oh sorry, X into WV is this, and this is WK. Okay, by multiplying our X, or the embedding, or embedding token embedding of AI, we get QKB of AI. Okay, and similarly we generate QKV of different tokens, like let's say Y is the embedding of AM, then QKB of AM are also generated using same thing, Y into WQ, like this, Y into WK. Okay, similarly every token maintains its own QKB values. Q means query, key means key, K means key, and value is V. Okay. Here, what these actually mean, if I would just want to tell you the semantic meaning of QKV. QKV simply means that the Q of I, or Q of AI here means that what query does AI has, or what it will, whenever we perform this formula, it is like what operation or what thing it wants to know from the other tokens is query, and key is what value or what knowledge AI token can contribute to other tokens is K, that is key, and V is value, means that what it will actually contribute when it, what we say, when we apply this formula over them, then what value it will be able to contribute to other tokens. These are the semantic meanings of QKB. and we apply these matrix multiplications here query. If I want to know attention of what we say attention for AI with AM AM token, I want to know the attention between AI and AM, or what AI will learn from AM. Then what we would do that we will take query of AI, key of AM, and value of AM. So when we perform this operation, we get one vector or one complete matrix, we can say ND. So this vector will have the knowledge of the connection between AI and AM. Similarly, we calculate same thing with AI and I. And if there are any previous tokens, we calculate for all. So many embeddings we calculate, many vectors we calculate, and if we keep these vectors on top of each other, then they are simply a matrix. So AI is all about matrix multiplications. Okay. So this is where QKV comes into picture, and this is feed forward. Once these embeddings, after this, these embeddings which are generated, these are again given to a normal feed forward, or the neural network which I showed you to explain what neural networks are. That neural networks may this is fed where here in our example neural network we had three inputs. Here we will have the input of the final embedding which we have. Each neuron will take the one dimension of the vector. Okay, and we will here have hidden layers in between, and then final output layer. Okay, this is what is feed forward. And here one thing to notice, this output layer or the output layer will have neurons of our vocabulary size. Vocabulary size means the number of words, or the words whose embedding we already know, or the tokens. I wouldn't say words, it would be tokens, number of tokens we know. Like byte pair tokenizer, which I told you initially, has up to I think 50,000 vocabulary size. So the output of feed forward will have 50,000 neurons, and these neurons, and the whole, after this whole process happens, attention and then feed forward, and after this the values predicted for each neuron will be the, I would say, it will be the number of each token. Here then we will apply softmax. Once softmax is applied, the whole dimension remains the same, but the value or the sum of these whole numbers will become 1. Now we got probability distributions of these. So here each, what we say, let's say it is at 0th index or 0th dimension. This represents 0th word in my vocabulary. Means that 0. If it is 0.1, then the next word, the probability of the 0th word in my vocabulary becoming the next word in my current sentence is 0.1, the probability. And this is the second word probability. Like that, because of that, we have the size of our output layer as vocabulary size. Each represents a value. Here now we will choose, either we will choose top K, given these are the parameters given by the user, or we can select them. Many LLM APIs now allow these parameters top K here, which what it means that now I got probabilities of different tokens being my next word. I got the probability. I hope you understood what these probabilities are. It is simply how much confidently the LLM predicted the next word to be this word, or nth word of the vocabulary. Now top K means what? Out of these all probabilities from vocabulary size, we would choose, let's say the values are 0.7, 0.8, and 0.9, 0.1. Let's say top k is 2. Then I would pick up two topmost or highest values. That is first, that is second word and third word. This is first word. This is fourth word. Okay. These are the probabilities. Then I would pick up second and third word and again apply some function on it and let the next word be predicted by LLM out of these two words. Or the other way is that keeping the top k as 1 means that the highest, the probability, means the word with the highest probability will simply be the next word. No need of thinking between top words. It is simply, it will help me to make the LLM output more creative, these kind of parameters. We have temperature parameters also. What is this temperature parameter? I hope you understood top k. If k is equal to 1, then simply we'll take the word with the highest probability and make it as our next word. If the top k is 2, then we will take top 2 values and again let the LLM, our more, we will keep some more networks or some networks here which will predict the one out of these two. Then we got, as you can see here, we got much more diversity or much more creativity. Here again LLM is thinking which word to give us next. That is top k, and top p is also there. Top p is like we were choosing in top k directly the top two values. In top p, what we will do? What of, I will tell you. Let's say top p is 0.9. Then we would go on selecting from highest to lowest. Like we have this probabilities, we will select the highest word, highest probability word, that is 0.9, and like this we will go on selecting till the sum of all selected words or the probability of all selected words, the sum of this, till the sum of this becomes top p. Now as you can see here, top p is 0.9. Then when I pick up the highest or take the highest word as my next word, it is already 0.9. And obviously I won't pick up the, or I won't take the next token in my consideration. Let's say if this value is something else, then I would keep on taking the value and adding up till the value becomes this. Once all the words are collected, again I would apply this same mechanism and let LLM select the next one. This is top P, top K, and temperature is one more parameter. The output layer gives the numbers for each, we say each token in our vocabulary. Then we apply these. Actually, I would say let you know one keyword, that this prediction is called as logits, logit, logit. And once we apply softmax and convert these values to probability distribution, once we apply softmax to these numbers or logits, it it is then directly called as probability, simple, nothing more. Or the final output of the LLM logits are the numbers predicted. These numbers are we apply softmax on these numbers or logits, and the final probability distribution which got generated, probabilities which got generated, are called as output or probabilities of the token of the LLM. Now temperature. What is temperature here? Whenever we apply softmax to logits, I said you the formula for softmax, I think. E power logit of I divided by sum of e power logit of j, and j is from 1 to what we say vocabulary size b. Okay. Now this value generated will become the highest probability in our final output. Okay. Now, what is this temperature? Whenever the temperature is given in this formula, we simply divide these values by that value, temperature, divide by temperature. So this exponent is simply divided by this parameter. What it does, it will again obviously mm, uh, change the probability distribution or make the probability distribution too close to each other. For example, softmax may after if I do only softmax and probabilities of two tokens are 0.1 and 0.9. Now if I apply this temperature parameter and then generate the probability, then the same probabilities would look something as 0.3 and 0.7. You can see they became much closer to each other. Now here when we apply top k and top p on these probabilities, LLM needs to think more because most of them are looking same here. So it will not allow. So by applying temperature, we will make LLM more creative and its tokens will be again the final output. We can control the what is a distribution of final output in the latent space. Let's move further. So we have seen now three parameters in the LLM and we have seen how LLM works at high level. I would like to show you the code for it. Uh, yeah, self-attention. Uh, Now, these are the configurations which will define how or what inputs, what are the size of the inputs which we would give to LLM and what are the size of outputs which we would expect from LLM. These are those configuration and the vocabulary size I was saying you guys. That also we have configured how much words we have in our vocabulary. And I have used byte pair tokenizer here. It is 50257. Context length, how much uh, length of input which we can give. This is 256. And embedding dimension, like I was saying, the initial vector which is generated here, input embedding, that is embedding dimension, and number of heads, this n heads. This n you can see here, this is n heads. And n layers. Sorry, these are the n layers. This is one layer and this is multi-head attention. This is one head. Multi-head attention, it has n heads, 12 heads it will be having. These heads will be 12 in multi-head attention. The formula which we have seen, K, Q, I showed you some formula, Q, K, T by Q, K, T into V by root D, the attention formula which I told, where is the formula? So anyways, this is the formula, yeah. This formula, this will be applied number of heads times, 12 heads, each head will apply one time, 12 times it will be applied, means let's not go into that. And N layers I showed you, and drop rate. This comes in feed forward, where in the neural network while training, we turn off a few, I would say we turn off a few neurons. We would directly make the weight as 0 here so that this and this doesn't interact. They are not dependent on each other. This drop rate is 0.1. It is done so that the our architecture or our neuron or any neuron doesn't depend completely on a single neuron. So this is drop rate and QKV bias. QKV bias, I would like to say as we are generating WQ, WK and WV. As I told you, these are like plain neural networks, QKV, which we have seen. And as I have showed you initially, y is equal to mx plus a, or normal neural networks depicts this only, or it represents this only. So this is intercept, or it is also, or we can say it as bias also, or not this. We will add one more parameter as bias here. Let it be different for clear explanation. I would say this is different, and bias, this is one more parameter, a tunable knob, which we can say, which will not completely rely on multiplications and allow addition. So B is bias, and QKV bias is simply as we have WQ, WK, WV, these are plain neural networks. Here, QKV bias means this bias parameter here. If we keep it false, like we have kept, then this won't be there. Simple. Otherwise, this is just for train local practice. Otherwise, this is generally kept as it is one more tunable knob, but we avoid that because it will obviously include more parameters and more load on our GPU. Okay, tokenizer. Here we can do text to token, token to text. Simply this we can do using byte pair tokenizers. And but by the way, if you guys want, you can comment and I will give you this code so that you can hopefully you can read this code with the help of using AI. If you guys don't understand this part, don't panic. This is not the part of inference engineering. I'm just telling you a high level view. Or I hope you guys understand the PyTorch syntax. This is the embedding layer. As I said, many architectures now directly introduce embedding inside the architecture itself instead of using some formula. So these are those parameters. And this is for token embedding. Similarly, as I said, positional embedding, these both will be added. The positional embedding is also kept inside the architecture only so that it trains along with the whole neural network. This is the dropout rate which I explained you. And these are the transformer blocks. Sequential means all the blocks will be executed one after the other, because if we have n blocks, as I showed you here, first this block executes, then one more clone will be there of this on top of this, then that block executes, like that n block executes. So that many we added, n layers. This is one layer. This is one layer, and like that n layers, and which we have kept in already configuration. This is coming from configuration. 12 layers we have kept, means like this 12 blocks will be there and one after the other, and not sequential means one after the other. These 12 blocks will be executed. Okay, I will show you this transformer block. This is one transformer block. This is only decoder based, not encoder and decoder architecture. Okay, now in this transformer or decoder block, what we can see: masked multi-head attention, feed forward, and these are normalization layers. Okay, I will show you that also. Multi-head attention layer. This is the one multi-head attention layer. Feed forward. This is here. Feed forward, which we have introduced. And in this feed forward, this is the feed forward layer, which we have introduced here. And layer normalization, which you can see this add and norm. This is that layer normalization. As there are 1, 2, 3 normalization layer. I think I have kept only 2, no issues. It depends on our use case. This is just for training part, by the way. Okay, normalization layer, 2 normalization layers, and forward layer. This executes the layers which we have made. Now this is multi-head attention. This part I would like to go into multi-head attention. Yeah, this is multi-head attention. What multi-head attention had, I showed you guys. Multi-head attention, it had Q, K, V, and that formula Q into K transpose into V by under root D, that is introduced here. Number of heads which we have taken already, number of heads in multi-head attention, and as I said, you WQ, WK, and WV will be made. These are WQ, KV, output layer, output by what we want. Again, dropout layer, which I have told you guys previously. This is mask. This is masked multi-head attention part. We mask our embeddings or in our inputs so that the current word doesn't see the future word in training. This is what we do, and these are executed. This is what the architecture at high level is. I have written the code, but I would like to explain this. But I would explain this when we are doing a proper LLM hands-on or creating LLM from scratch. Now it is completely not useful for inferencing. So I said you temperature, top K, top P, and about this, I have said you what are the architectures, how would the code at high level look like. Please comment if you guys want this code. I will surely give you guys this code. And let's continue. Regarding the parameters, I would say temperature is introduced, Q top K, top P are introduced in inference engineering. That I have covered in depth. That was actually required for inference engineering. And one more thing I would introduce is that the lower the temperature, top K and top P value, this makes the LLM more predictable in predicting next tokens, because the higher the value, the higher the values of these parameters, the closer the probabilities would come to each other. So it would be difficult for us to predict which will be the next token. But as I said, if these are the jump values or high gap values, and we don't introduce these top K, top P, and temperature, then it would I can directly say that it would pick this value. But if we have these things, other parameters, top temperature, and those things, it will be difficult for us, as these values won't look 0.1 and 0.1, 0.9. It would look close to 0.3 and 0.7. Or even if we increase more the value of temperature, and that it would become 0.4 and 0.6. Now, when it goes to neural network to predict next word out of these two words because of top K and temperature, then it will become difficult for us to predict. If the gap is high, even if goes to neural network, we are sure that it will predict this. So that kind of customization and creativity we can provide just by these three parameters. Okay, LLM architectures I have introduced you. You guys can see these models or download these models if you guys have GPUs, or at least small models. SLMs you can download. And anyways, models are of different sizes. These things which I have showed you, this config part, this is generally when you download a model from Hugging Face, you would get these things automatically, because they would keep this as blueprint of their model architecture. Like what is the embedding layer, how many embedding layer are there, what is the context length. This is the kind of map, or it will be mostly named as config.json, which will introduce this, which will show you these information. And models are obviously of different type. The base model which I have currently, this one, and the other model is instruct model, where we, once pre-training is completed, we again do post-training on our what we say instruction basis. Many data sets are there for that also, and reasoning basis we train that. See, pre-training is just to make the model or the attention weights or W or QKV in the model, WQ, WKWV, to know what is the text, what is the general meaning of text, how to interact with the text. That is introduced in pre-training. Then how to interact, like whenever you ask the question with GPT, it will explain you the answer and ask a follow-up question. These things comes from instruct based training. We instruct it to do particular or ask in a particular way or behave in a particular way. Otherwise, it would just simply give random text which we can't understand. And these inputs are not only text inputs, we can give audio inputs. In this, text inputs may include audio signals also for audio models like Whisper. It would include image pixels for image, or for vision models, vision transformers. And image generation models are also trained on this. We will cover that in second part. As you can see, this only became too big. Now image or diffusion models are much more not much more complex, but that is a complete different paradigm in AI. And I would say one more thing, that whenever you see a model, for example, if you have a model named as, one second, let me close these things. I am also sharing directly the resources in my videos. So I would like you guys seeing the or reading these resources to get a much more better understanding. Let's say you have Quen 3MOECASUAL. Quen, and I would explain you how to read these names. Quen, the base model, Three, the version of the model or the major version architecture within the family of when. MOE means it indicates that a mixture of this model is a mixture of experts model. Now after this I will explain mixture of experts also. And causal LLM means it is normal causal language model, means it predicts next word, and it has masked attention so that it doesn't cheat by seeing the future word. This is what the name means of LLMs. Okay, now let's get into MOE. As the transformer blocks are done, let me recall what things are done. Feed forward is done. Attention I have explained. Attention QKV. Softmax is applied. Yeah, these things are explained. And yeah, one more thing is this which I explained was self-attention. If you can see, in attention is all you need. Attention is all you need. Here at ChatGPT, it has only decoder models. Decoder are applied on top of each other, stacked on top of each other. This is what we call as self-attention model, where each word learns from the same sequence, or it introduces itself and gets knowledge from other tokens from the same sequence. But the other paradigm is cross attention, where, as we saw QKV, in cross attention, this Q comes from a different sequence as compared to K and V. This is called conditioning Q on external information. This cross attention is generally uh, found commonly in encoder and decoder architectures. Not only decoder, in encoder and decoder it is found. I have written a basic code for cross attention also. This is what it is. Yeah, this is what it would look like. I will compare and show you in a better way. 1 second. Multi-head attention. This is self-attention. This is Q, W, Q, K, V are trained and the formula is applied. Where is the formula applied? Here. This is the formula being applied. Causal mask attention score. Yeah, Q into KT. I said, Q into KT. This is what it is. Query into T transpose. Q, KT. Next is causal masking, mask will okay. And into V. Multiplying it by V. Okay. This is what it is in multi-head attention. Now I will show you cross attention, multi-head cross attention. Here it is. Q comes from decoder and K and V are found in encoder. So as I said, encoder decoder architecture has cross attention mostly. That is only the difference. It comes from decoder and these comes from encoder. Rest formula also remains the same. I will show you that also. The formula also remains the same. Only the thing coming is from other sequence. Formula also remains the same. Into V, everything remains the same. Okay. This is encoder decoder. This is decoder decoder. Now let's move to mixture of experts. As we have seen till now, in a neural network or in attention, we have a huge number of matrices and parameters. What this mixture of experts solves is, let's say we have a neural network with so many hidden layers. Then if I want to run some small query also, all these weights will be activated, or so many matrix multiplication will be happening, and the output comes, which gives a high load on GPU in terms of both memory and compute. So we introduce MOE, mixture of experts. Here what we do generally, instead of only what we say, instead of invoking all parameters, we introduce a one more layer, a router layer, ROUT, router layer. Like you saw, embedding layer is trained inside the architecture only. Router layer is also trained inside the architecture. Let's say we have dense neural hidden layer here, and half of the part is dense neural network. And this router, okay, this router takes the input, and it is also trained along with these neurons only to give the output. It takes the input and it outputs a vector of or array or vector of size number of experts, NE I would say, number of experts, where expert is one big bunch of neural networks. This is one bunch of neural networks. This is one big bunch of neural networks. Normally, what we would do, take the input and apply whole matrix multiplication on all neurons and give the output. But it is waste to invoke all the neurons. I would here router is trained to invoke only the neurons which are the best suitable for this input. So it would give me this, the router would give me vector of two numbers. Let's say it is 2 and 3, it gave me. Then again I would apply softmax to convert this into probability distribution. Then it would become something like 0. Let's say 4 and 0.6, just an example. And as the probability of the uh, second expert is high, it means that I would send the request and I only invoke the second bunch of network. The query goes here, processes it, and gives the output. So we have saved the computation over here. Like that, I showed you two experts. There are like that n experts. N can be, I would say, thousands or lakhs also. Like I would say that the original, I would first show you the code instead. MOE.py, yeah, this is the code. Expert, I said you, what is an expert? A bunch of neurons and neural networks. Here I made an expert where n sequential means layers will be executed in the sequential order. Here it is n linear, ReLU, and then linear means that an expert looks something like this. It has one linear layer, one ReLU activation function, and again one linear layer. This is one expert, and the size or the number of neurons in each layer is this. Input dimension, hidden dimension. Okay, means that it would take hidden dimension input and give it would take input dimension input and give hidden dimension size. This is one expert, and as I said you, instead of invoking whole neural network, we divide the neural network in experts. And actually, we won't divide. We will just introduce expert layers and let the router decide which expert should be invoked. Now, we have made these bunch of neural networks under the class expert, and in MOE, I will make, let's say, I said you lakhs of experts can be there. I would take number of experts as input and make that many experts in my list. Module list is just a container to store the PyTorch neural networks or PyTorch layers, I would say. So here, this is one expert, and this each expert is bunch of neural networks. Okay, here. Now I would introduce that many experts, and router, as I said, router is also a linear layer. It is introduced here, and it will output a vector of size, number of experts. This is that, and this is the router linear layer, which outputs a vector of size, number of experts, where each probability points or means the confidence of calling the ith expert. Okay. Now we do the plain back propagation and training here. I would show you that also. Yeah, in forward, we will call the router layer obviously first. That router layer may we apply softmax to convert into probabilities, and out of those, I would say, or I would call the maximum one, and then invoke only that layer. But currently, this was the original paper which introduced calling all the experts and nullifying the other experts. Let's say I have n experts, then I would use only two experts, and I would obviously call all the experts, but I would take output of only two experts and remove all the things, because this paper mostly focused on quality of output. But then the same thing was modified to, instead of invoking all experts, I would invoke only two experts. Initially, instead of like initial we did, we called all the experts and nullified effects of all the irrelevant experts. Then, but to make it computationally effective, people made a change that instead of calling and nullifying them later, we won't call that expert on. So that was changed, that I will show you here. Then, and only call the particular experts and get the output from them, give it as the output. This is what it looks like. I will train it on number of epochs and something. As I said, later it was modified to, instead of invoking all experts and nullifying them later, I would invoke only the particular ones. Now, which one to invoke? I know which one to invoke. I know the probabilities of top, what we say, top experts. I know the probability of top experts. But the question is, should I invoke only the topmost experts, one expert, or invoke top two experts and then combine those answers for a better output? That is completely our choice. So because of that, we use top K, like we introduced in LLM also. Top K was introduced. Here again, after doing softmax, I would take top K logits or top K values from this router output, and call those top K experts only instead of calling all. So to stop from calling all, I would make others as zero, other weights as zero, and then call it simple. That is top K. Top one routing is calling only the topmost expert, or we can say the highest probability expert. So here one topmost expert is called, and in MOE.py all experts are called in the original paper and nullified later. In top K experts, we only call the, what we say, we only call the experts which we want, or the top K experts which we want. This is what was MOE.py. Now, one more game. This was introduced for neural networks, but then there is a architecture in transformer called as switch transformer, which was introduced as WITCH, switch transformer. What it does, as we have seen in attention, we do multi-head attention and then call feed forward. Instead of directly calling feed forward, first we call multi-head attention, as we always do. Multi-head attention is called. Then instead of directly calling feed forward, we keep a router here. ROUTER, router. This is attention layer. This works as it is. Multi-head attention is done, and then the router was introduced here in switch transformer. So instead of directly introducing or directly invoking all the neurons from feed forward F F N, instead of directly invoking all the neurons in feed forward, we introduced a router. Here the attention weights or embeddings goes here. Then router is obviously trained in the along with the architecture. It again generates logits, which we say the numbers of each experts. Let's say F feed forward later was divided in n experts. Then this value is n. N numbers are generated. We apply softmax to it. After applying softmax, yes, these numbers are converted into probabilities. Then then in our architecture we introduce call the top or top one expert directly, or to call top k experts directly, that is what is in our hands. We introduce here. Okay. So this was introduced to make the what we say to make the inference efficient. This was one thing that was introduced, and this was mixture of experts. And the other thing was KV cache. Like we saw, Q, K, V values are generated every time for each token. Let's say I have what we say three words. Like I said, I am AI. Then every time I would generate QKV between I and M, and AI and I would generate, let's say one more word got added, and again I would calculate am and AI and I, and then calculate this. Again, we every time whenever the new word is added to the sequence, we every time calculate the K, Q, V of the previous tokens also, which is useless as they would remain same only. As the previous tokens are same, they would remain same. So we started caching the values or the KB, the QKV values of each of them. Once they are generated, we will store them in memory and only calculate the QKV of the latest one instead of calculating for all. This was introduced. I would like to show the code in the future lectures because in the book it is not introduced now. It is introduced in future chapters. I just told you a high level view of it. I will show the code in the later chapters. So this was that, and similar things we would cover for image and what we say image generation and video generation also. Let's move to the inference bottlenecks. We saw the architectures. We saw that compute and memory are our what we say bottlenecks. So what is compute? Compute is the number of floating point operations per second, or flops. LOPS. OPS, floating point operations. Floating point operations. This is like the number of floating point computations per second a GPU can achieve is called as flops, and the memory is measured as the number of bytes the GPU can move per second. So the compute is flops FLOPS per second, and memory bandwidth is number of bytes per second a GPU can move. So the compute metric is generally measured by operation, number of operation per byte. As we can see, number of operations is defined as flops per second, and byte and memory is defined as bytes per second. When we divide them, the seconds got cancelled. It became flops per byte. Okay. This is what we measure to see how efficient a GPU is. Now, as an inference engineer, our task would be to optimize in both compute and memory terms, like in both prefill phase and both decode phase. Prefill phase, now I can say you that the KV cache which is generated, the embeddings which are generated, comes under, or the attention mechanism which happens comes under prefill phase, and the next rest of the part comes under decode phase. As you can see in prefilling, we are generating KV cache. First time whenever we calculate a word, we generate key and value for it and then cache it. So here we are using what we say here we are using our compute to generate K, V and Q. So mostly prefill phases compute bound and decode phases memory bound. As here we would in decoding or generating the new word, you would just use the saved cache. So that many weights should be loaded into the memory. So decode phase is mostly memory bound. And image and video generations are also compute bound, that we'll see in next part anyways. And to check in our neural network whether it is what we say efficient, or whether our neural network or our algorithm whichever we are introducing is memory bound or compute bound, we would use a metric called as intensity, that is equal to work per memory traffic, empty memory traffic. What is this intensity here? It simply means that how much work our algorithm can do in some memory traffic. That is called as intensity. If our intensity of our algorithm, which we calculated using this logic, work done per memory, if that intensity is higher than the GPU power, GPU power is this one which I showed you here, what flops per byte, this one. This flops per byte is GPU power. If our intensity of our algorithm is greater than GPU power, that is our flops per byte, flops per byte, then our our algorithm is simply compute bound. COMPUT. As you can see in pre-fill phase, if we calculate intensity and check the GPU thing, then our our attention and those things and pre-fill phase is compute bound and decode phase. And if intensity is less than the GPU power, then it is memory bound. Okay, this is a plain metric. And we have also seen the different metrics to measure compute like TTFT in previous video. I will attach it on the I section above. You guys can see that TTFT and TPS, token per second, time to first token, and different TPS were introduced in that video. You guys can see that. Next thing is as KV cache is introduced, optimizing things are introduced. Now, as we have seen, KV cache is one thing to optimize attention mechanism and transformer mechanism. Writing high performance CUDA kernels that we would do mostly in hardware lecture, writing CUDA kernels or introducing new algorithms like KV cache was introduced in, or MOE was introduced in transformer. These things come under new algorithm introduction, and writing the same architecture in efficient way using CUDA directly for GPU level is one way. Okay, I showed you MOE already, the code for it. This is one improvement or new algorithm introduced in transformer for optimization. Hardware related things and CUDA related things in the same future. In the mostly it is in third chapter. After part 2, I will cover that third chapter also. Also, one heads up I would like to give, or one curtain raiser on these CUDA kernels, that there are or you can refer this before seeing that lecture or before I make that lecture. You guys can also be prepared. Flash attention. Flash attention. These are the series of attention mechanisms or different LLMs. Means that we had GPT. Let's say we had GPT. Instead of introducing new algorithms like AV cache or MOE to it, we directly, instead of writing this, like I wrote here, self attention in PyTorch, the same code, if we write in CUDA, that is what is flash attention. Flash attention is a series of different papers, or I would say our basic algorithm implementation with handful of lines of code. Means this handful of lines of codes are converted into thousands of GPU level code in flash attention using CUDA to make it efficient on H100s and B200 GPUs. So that was one thing which we will see in hardware layer instead of directly. Instead, we will convert. I will try to convert a kernel level implementation, which will obviously speed up the thing. And if we introduce KV cache and those kind of algorithms in this MOE and those kind of things in this, and then convert it into kernel level or CUDA level, then it would obviously become more fast. I think many flash attention already have that. We'll try to cover it in that. Now, anyways, that was one thing. Now, new algorithms may we discussed MOE and KV cache. More things which were introduced were sliding window attention. Like we saw, let's say I have I and AI. Okay. Then in sliding window attention, let's say sliding window length is 1. Then here what we do, whenever a new word is introduced like AI, we calculate QKB with other tokens every time. Now, what sliding window suggests that instead of calculating with all the previous tokens, just maintain a window of size 1 or n. Here we have 1, and calculate QKB only with the tokens inside that window and leave all the tokens outside the window. Because here calculating with every token, let's say we have n tokens and it is calculating QKV with every token, so the complexity will be simply n square. Now when we introduce a window, then it would become n into w, where w is obviously less than n. Okay, this was one thing, sliding window attention. Then they introduced gated attention. Different types of layers were introduced to chunk the inputs directly before sending it to feed forward. And linear attention, where now we saw in our attention we introduced softmax. So instead of introducing softmax at different layers, they introduced linear time algorithms, different algorithms or different functions in linear attention. And then there are many more architectures like compressed attention, multi-latent attention. Like multi-latent attention is like it what it does is it simply takes a bigger embedding and narrows it down into smaller embedding, uh, or not, or smaller embedding, and along with that it would also generate probability distributions like mu and sigma were introduced. And these were also calculated. This will see in latent this will see in diffusion models also. These were VAE, they introduced this and reduce the size of embedding in the latent space. This you will see in vision part, in the part 2 of this video. So like that, many hybrid architectures were made, many GPU specific kernels were made for these things. So these were optimization techniques for and how normally text LLMs work. This was a detailed view of it, how much ever I could provide. And as we are focused on inferencing, I didn't focus much on math. I tried as much as I can, but if you guys are interested in that, please select or vote for a book in my recent YouTube post so that I can know whether you guys are actually interested in creating LLMs from scratch and those kind of mathematics, probability statistics. If you are interested, if you guys actually want to learn this mathematics, you can comment a few mathematics book on that post so that I can come up with a few lectures on mathematics books also. Or if you guys are interested in some other technological book, please comment so that we can decide what you or I can decide what you guys are more interested in. This first book was of my choice as I liked this concept and it is the future that we can see today already. So, all the best, and let's meet in the part 2 of this lecture.